Stanford Binet test. I remember being amused. I thought these engineers love numbers, and they want to put a number opposite each of the scientists, which they had. I didn't think anything much about that until much later in the game. I then got to my research assignment, which had to do with the electromagnetic method of separating the components of tuballoy. Tuballoy was the code name for uranium, and we appropriated that from the British atomic bomb project. The British had started a project, but since they were deeply involved in the battle for Britain, they had to abandon it. Our group did acquire 2 British scientists from that project, however, and we undertook, tongue-in-cheek, to teach them proper English. The 2 of them shared an office, and so we put banners up around their office: lift equals elevator, lorry equals truck, and so on. They in turn complained if they didn't get the results they had expected for their experiments about the inferior American equipment they had to work with. But we got on famously. The bulk of the research group was recruited from the University of California at Berkeley. And it was a high-powered group. I remember 2 of my colleagues would walk down the street. They were chess fans, and they would play chess as they walked down the street. They had set up an imaginary chessboard, and they located the positions on the board by letters and numbers. But this was not a 2-dimensional chessboard. It was a 3-dimensional chessboard. And so they played 3-dimensional chess on an imaginary chessboard while walking along. And they took the game very seriously, because weeks later they would argue, what if you had done this instead of that, and so on. But they were an unusual group, and it was a pleasure in many ways to be associated with them. If we look at the picture of the device, you get some rough idea of the method that was used successfully to separate the uranium isotopes, uranium-235 from 238. The source material was a green solid uranium tetrachloride, tuballoid tetrachloride it would have been called in those days. It was heated and vaporized to give uranium vapor, both a mixture of 235 and 238 uranium. It was ionized and then accelerated by a electric potential of about 2,000 volts. And then the beam of uranium ions was deflected by a very large magnet. The magnet, incidentally, that was appropriated from the cyclotron at the University of California, the largest magnet in the world at that point in time, or the most powerful one. The lighter uranium-235 ions were deflected more by the magnetic field than the heavier 238 ions. And unlike this picture, there was not one collector, there were 2 collectors, which were called the Q pot and the M pot. We joked that the Q pot was the quap pot, which collected the not very useful uranium-238, and the M pot, the money pot, which collected the valuable uranium-235, the fissionable form of the material. Notice, if you will, that the entire device had to be evacuated because air molecules would have deflected the path of the ions. This was so-called Y12. Everything was given fancy numbers by the intelligence people. So in Y12, the electromagnetic separation of uranium isotopes took place. Also at Oak Ridge, there was a gaseous diffusion method in which gaseous uranium hexafluoride was passed through a barrier containing very fine holes. The light isotope would go through the hole more readily than the heavier isotope, and so there would be a slight enrichment in the uranium-235. The slightly enriched material would then go through a second barrier, and then a third and a fourth, and a tremendous number of consecutive barriers. That was a gaseous diffusion method, or K25. That never completely enriched uranium, but the partially enriched uranium was used as starting material eventually to make the green uranium tetrachloride charged in the gadget. This gadget, incidentally, was called the calutron because it was devised from parts obtained from the University of California cyclotron, calutron. And I found out why Sam Arnold was so quick to recommend me for the project, because the source material, the uranium tetrachloride, when it was only about half vaporized, lost its volatility. Apparently, it was changing its structure with high temperature. And Arnold remembered my studies of tin, which changed its structure at low temperature, and thought I would be one to work on this project. The production of uranium-235 as a result was slowed to a crawl because this picture doesn't do justice to the size or complexity. Let's see if we can get a better idea. This was the device under construction. It's called a racetrack. You can get some idea why. The curved track around which the ions were deflected. Those are stairways leading up the side, so you get some idea of the scale. That whole massive structure had to be evacuated so that the air molecules wouldn't deflect the ions in their path. The path, along the path, the voltage had to be carefully regulated. And you see the row of young women, mostly Tennessee farm girls, which could unkindly be called hillbillies, involved in running the most sophisticated of equipment. Their duty was to look at the dials and adjust switches, and you see they watch the dial and adjust the switches to keep the voltage constant during the course of the run. Notice, if you will, all the women involved. It's not generally known, but the great majority of the plant workers made the first atomic bomb were women. And that is shown, this is a shift change. Notice, not on, oh, there is a male, a lone male over here. Incidentally, I was able, once I had arrived and joined the research group, I was able to send for my new bride, Pat, who joined me at Oak Ridge. Thanks to her secretarial skills, she had no trouble getting a job. He was secretary to the man in charge of the Calutron during the daytime shift, fortunately, because the Calutron, along with everything else in Oak Ridge, ran 24 hours a day, 7 days a week. There was no idle time. It was after a run was completed, the very precious uranium-235, or even partially enriched uranium, had to be saved. It was washed down off the sides of the container and recovered. And here you see liquids in bottles. Notice the women here are wearing white uniform. All people who worked with this uranium were given white uniforms to wear. The uniforms, new uniforms, were given to them at the beginning of the week. At the end of the week, the uniforms were retrieved, incinerated, and any uranium obtained from the ashes of the incinerated uniform. Even the people in the lab, I was included, had to wear these white uniforms because it cost $2 billion to make 40 pounds worth of uranium-235. That is very precious stuff. And in those days, $2 billion was real money. Now it would be, what, 1 week worth of rock. This is an aerial view of Oak Ridge and of Y12. It does not include K25 or X10. K25, as I mentioned, was the gaseous diffusion process. X10 was where experimental methods were tried. They tried every method they could think of for separating uranium isotopes at Oak Ridge. And X10 was the site of some of the experimental methods. One of the experimental methods was a centrifuge. If you spin a gaseous form of uranium hexafluoride rapidly, the heavier isotope would gather at the outside of the tube and the lighter one at the inside. This never worked because it was not possible to construct the centrifuges precisely enough. There was some wobble as they spun, and the wobbling remixed the gaseous material, so that the centrifuge was an unsuccessful method that was tried at X10. However, thanks to computer-assisted machining processes, we can now make centrifuges much more precisely. And the centrifuge is the method of choice at this point in time for separating uranium isotopes. And as I speak, there are at least 1,000 centrifuges spinning merrily in Iran, enriching uranium. They claim for peaceful purposes. At any rate, since the uranium tetrachloride going back to the Calutron was useless after only half of a run, and since there was a great deal of effort that had to go into recovering the partially enriched uranium and recycling it, and since this huge structure had to be evacuated each time before a new run could be started, production of uranium-235 had slowed to a crawl, and it would have began to appear as though they would not be able to make enough uranium-235 for a bomb. And that's when we were brought into this research group. At one point, to show you what kind of priorities the Manhattan Project had, we decided we needed a scanning electron microscope. At that point in time, scanning electron microscopes were just beginning to become available commercially. There were perhaps 6 in the whole country. 2 of those 6 appeared at our lab within a week after our request. So they were going all out. Thank you. My wife looks after me. So production had slowed to a crawl. We learned, incidentally, that it was the method of manufacture of the uranium tetrachloride that was at fault, because the material which came to the calutron from the manufacturing plant, one of these many plants, was a mixture of 2 crystalline forms. One form not volatile, the other form volatile. So only after half of the material had been volatilized did the material stop, because the non-volatile form was left behind. Incidentally, the uranium tetrachloride was made in a building which the denizens of Oak Ridge called the Flash Gordon building, because it was a very futuristic looking building. The entire roof was covered with an array of ventilating pipes, and the air in that entire very large building was changed every few minutes in such powerful blowers. This was necessary because the method of production was to heat carbon tetrachloride with uranium oxide. This generated uranium tetrachloride, all right, but the byproduct was phosgene gas. Phosgene was one of the most lethal gases used in World War I. And in spite of the huge ventilating system, the workers in that plant, poor folks, had to wear gas masks during their entire 8-hour shift. Well, our group determined that that method generated uranium tetrachloride at high temperatures, and that's what gave rise to the large amount of the non-volatile form. So an entirely different method of manufacture had to be devised, and that started with gaseous uranium hexafluoride, which was available in K25, the gaseous diffusion method, and the result was the Flash Gordon building had to be abandoned. This very expensive building was just left idle, and a new building rapidly constructed for the manufacture. But the result of the changes was that the amount of uranium-235, the production of uranium-235 was approximately doubled, and they were back on track. July 1945, word came. Let's see if I have a picture. Oh, here's some pictures. These are the vacuum pumps which were used to evacuate the huge racetrack. And you see the large array of vacuum pumps running continuously. The noise was deafening. Here's a picture of you-know-who standing next to that magnet, the famous magnet. This was taken in 1972. The head of our research group was a professor from UCal Berkeley, And in 1972, he was kind enough to invite me to join the faculty of the University of California, Berkeley, as a visiting professor. And there I found this famous magnet as a museum piece. I couldn't resist having my picture taken with that famous magnet. The picture taker, unfortunately, got too much of me and too little of a magnet in the picture, but you get, I think, the idea. Incidentally, when I was at Berkeley, my office was next door to the office of Glenn Seaborg, the man who invented plutonium and who won the Nobel Prize for his effort. And to my great appreciation, Seaborg was not hidden from the undergraduate students. He was assigned a section of freshman chemistry to teach, and 3 times a week he had office hours, and he helped the students with their problems. That was great to see, because most Nobel laureates are hidden away from the students and not given anything to do except their own research. Incidentally, before it was learned that it was the manufacture of the uranium tetrachloride that was at fault in the generation of the U-235, a natural solution to the problem was to build another magnet and double the number of calutrons. This sign is in front of Y12 at Oak Ridge now. You can see the picture is in color. We now have color pictures. Back then it was all black and white. And notice the sign says that they needed some silver. They said because they couldn't get copper. I think the real reason is silver is a much better conductor of electricity than copper. And so they borrowed 14,000 tons of silver from the U.S. Treasury. And if you remember, during the war, at one point, we used to have silver coins. We stopped having the silver coins because that silver was going into the production of a second magnet. The construction of the magnet, for some peculiar reason, was given to a subsidiary of General Electric instead of the scientists at the radiation labs at UCal Berkeley. And they were never, the General Electric people were never able to build a decent magnet, silver or no. That takes us to July 1945. And word came to our laboratory, much excitement, that the plutonium device had been tested successfully. And this was accompanied by a piece of green glass, which we were told was the sand under the tower in Alamogordo, New Mexico, which had been fused into glass by the heat generated by the plutonium device. The gadget, it was called, and this was the gadget. Notice the spherical shape, the same shape as Fat Man, and the implosion to form a critical mass of plutonium. We passed the glass around with gay abandon in the lab until somebody thought, let's put a counter on this, and it went off scale. It was very radioactive. So then we treated it with respect, which it was due. Shortly after that came word from the Army, we have a bomb, it works, there'll be no more basic research. So here are all these scientists, some of the best in the free world, sitting around, ordered not to do any fundamental research. Incidentally, there was always tugging and hauling between the scientists and the military. I can say that because by this time, about halfway through my stay at Oak Ridge, I was promoted to civilian. I think they didn't quite know what to do with me. Uh, for example, we were told we must not talk to fellow scientists in other laboratories. They tried to divide everything in tight little compartments. We, on the other hand, were very aware that the Germans had an 18-month head start on us. And we knew that we'd be wasting time if we duplicated work done in other laboratories. So in spite of that, we had clandestine meetings with the other research groups and exchanged notes and ideas. Also, one of our group at one point had an experiment going. He went back to the laboratory and worked till the wee hours of the morning. Naturally, the next morning he came in late, about 10 o'clock. He was seen by the military coming in late, and they were outraged, and they threatened to put in time clocks and have us punch in and out. So we got together, and the next morning we sat around reading newspapers. We all showed up on time, but we read newspapers. And they said, "What are you doing? You're paying us to think we're thinking." They got the idea. So there was always this tugging and hauling. Incidentally, soon after word of the successful test, I was called in by Colonel Ruhoff, who was the works manager of Y-12. In civilian life, Ruhoff had been the CEO of Mallinckrodt Chemical Company, one of the largest chemical companies. And Ruhoff asked me all kinds of questions about chemistry, physics, and math, and it was obvious his knowledge was not very deep. So I gradually made my answers more and more detailed, and more and more technical. And he finally stopped and he said, "Would you work out of my office, get production figures from all parts of the operation?" And as you could see from the aerial view we saw, this was a pretty extensive operation. Get production figures from all parts of the operation every morning, identify bottlenecks, and go out and devise a cure. Well, this was not too tough a problem because invariably where something broke down, somebody simply hadn't followed instructions. To give an idea, I was sitting in my desk one morning after I had my fancy new job, looked out the window, and there was a loading dock in which workmen were stacking 55-gallon drums of solution containing partially enriched uranium. There were circles drawn on the loading dock, and the instructions were to put a drum in each circle, but not in between, so that they would not unwittingly assemble a critical mass of material. To my dismay, I saw the workmen piling the barrels one on top of the other. They had filled all the circles, and so, obeying instructions, they were putting the barrels on top of each other. I dashed out and found the foreman and told him, no, put the barrels outside the loading area, an equal distance between as the ones on the loading area. So that was generally the idea. The people had no idea what they were working with. They had instructions to follow, and sometimes they bent the instructions a little bit. However, because the operation ran 24 hours a day, 7 days a week, it was a brutal, brutal job, because invariably the problems would be on the graveyard shift. I acquired a number 6 security badge which was the highest security. That is, I had access to all the information available. And I could go everywhere. One of the first trips I made was to visit Pat at her office at the Cagatron building, which they called refining, non-committal. They didn't say what they were refining. But I was dismayed when I got out into the plant because the workers had not been told the nature of the material they were working with. Uranium is radioactive. It can do great damage if not shielded properly, and if taken internally, it can destroy the person involved. And so I tried to warn as many people as I could about what they were dealing with and what basic precautions to take. Even in our laboratory, there was considerable radiation. I remember at one point, someone got the idea of putting up a radiation detector in the lab and attaching it to a siren. And when the siren went off, the instructions were, drop what you're doing and get as far